So, let's talk about something that sounds like science fiction, but is happening right now. How does a massive global network like Bitcoin, with no CEO, no central office, not even a single server in charge, actually agree on anything? How do thousands of computers that have no reason to trust each other all keep a perfect, identical record of every single transaction? This isn't just about crypto, you know. This is a huge question for everything from supply chains to the future of the internet itself. And the answer is this incredible concept called distributed consensus. So here's our game plan. We're going to break down what distributed consensus really is. We'll start with the basic problem of just getting everyone on the same page. Then, we'll look at what happens when things go wrong. First, when computers just crash, and then when they start to actively lie. After that, we'll connect the dots to the real world, see how this defines different types of networks, and even look at how big businesses are using this tech right now.
All right, let's dive right in with the big one, the agreement problem. How do you get a group of independent computers to agree on a single source of truth?
Think about it like this. With your bank, it's easy, right? There's one central authority, the bank itself, and it has the master ledger. That's the one and only truth. But in a decentralized system, everybody has a copy of the ledger. So how in the world do you make sure every single one of those copies is exactly the same all the time, when there's no boss telling everyone what to do?
And that's where distributed consensus comes in. It's basically the engine of any decentralized network. You can think of it as the digital rulebook that every single computer has to follow, no exceptions. This rulebook makes sure transactions are valid, that they get recorded in the right order, and most importantly, it stops anyone from going back and messing with the history. It's what makes a trustless system actually trustworthy.
Now, for any network to work, it's got to be tough. It has to handle failures. And, well, the simplest kind of failure is when a computer just gives up.
We call this a crash fault. It's pretty straightforward. It's like a server gets unplugged or its Wi-Fi goes out. The computer is just gone. It's silent. It's not trying to cause any trouble, it's just offline. And honestly, this is a pretty easy problem to solve, because you can basically assume that all the computers that are still online are playing fair.
So the solution is to build systems that have crash fault tolerance, or CFT. This just means the network doesn't have a total meltdown just because a few computers go offline. The rest of the group can just keep on working, reach their agreement, and keep the whole system running like nothing happened.
Now, computer scientists have come up with some really clever ways to do this. There are algorithms like Paxos, but a more popular one these days is called Raft, because it's just easier to understand. Raft is pretty cool. It works by electing a temporary leader. That leader proposes a new block of transactions, and all the other follower nodes just have to agree with it. Simple. If the leader crashes, no big deal. The followers just elect a new one. It's super efficient, and it works perfectly, as long as you can trust everyone not to lie. But what happens when you can't?
And this is where things get really, really tricky. What happens when a computer doesn't just crash, but it goes rogue? What if it actively tries to sabotage the whole network?
This, my friends, is called a Byzantine fault, and it is the absolute worst-case scenario. A Byzantine node is an active enemy. It can lie, it can tell half the network one thing, and the other half something completely different. It can invent fake transactions, or even team up with other bad guys to try and take over. This is pure chaos.
To even begin to understand how to solve this, computer scientists came up with a famous analogy, and it's been a classic for decades: the Byzantine generals problem.
Okay, picture this. A bunch of Byzantine generals have a city surrounded. They have to coordinate their attack. If they all attack at the exact same time, they win. But if even one attacks at the wrong time, they all lose. Their only way to communicate is by sending messengers. Here's the problem. Some of the generals might be traitors. A traitor could send a message to one general saying, "Attack at dawn," and another message to a different general saying, "Retreat at dawn," completely wrecking the whole plan. So how do the loyal generals agree on a plan when they know some of the messages they're getting could be lies?
The solution to this puzzle is a system that has Byzantine fault tolerance, or BFT. A BFT system is a fortress. It's designed to work perfectly even if a chunk of its members, up to a third of them actually, are actively trying to bring it down. This is the absolute gold standard for creating trust when you can't trust anyone.
So this really makes the difference crystal clear. CFT is for systems where you basically know and trust the players. Like inside a single company, you plan for accidents, but you don't expect sabotage. BFT, on the other hand, is built for the Wild West, for public networks like Bitcoin or Ethereum where anyone can join and you have to assume some people are out to get you.
The choice between these two models pretty much defines everything about a network.
Okay, so let's take these technical ideas and see how they map onto the two main kinds of blockchain networks you always hear about.
This table really says it all. You've got your permissionless public blockchains like Bitcoin. Anyone can join, so they must use that super secure but slower Byzantine fault tolerance. That's a big reason why a Bitcoin transaction takes around 10 minutes to confirm. But then you have permissioned or private blockchains like Hyperledger, which are built for businesses. In that world, everyone is known and invited. You don't have to worry so much about traders, so you can often use much faster algorithms like Raft. That's how they get transaction speeds down to just a few seconds.
All right, so how does this actually play out in a real business network? Let's pop the hood on one of the most popular frameworks out there for private blockchains.
So, Hyperledger Fabric is a big deal in the enterprise world. It's an open-source project hosted by the Linux Foundation, and it's designed specifically for businesses. Think of a group of different companies all trying to track a shipment of goods across the globe. They're working together, but they don't necessarily trust each other completely. That's the perfect use case for something like Fabric.
Fabric has this really smart way of handling things to stay fast and secure. It's like an assembly line. First, someone submits a transaction. Next, a few designated endorser computers check if it's valid based on the rules. Once it gets enough thumbs up, it goes to an orderer. This is the key part. The orderer uses a fast consensus algorithm, like Raft, to put a whole batch of transactions into a final guaranteed order. Then, that new block gets sent out to everyone, and they all add it to their ledger. It's a clever process that gives you both speed and security.
Okay, let's zoom out and put a bow on all of this. We've talked about crashing nodes, lying generals, and different kinds of networks. But what it's all really about is trust. When you get right down to it, the consensus algorithm isn't just a piece of the puzzle. It is the puzzle. It's the very heart of a distributed network. It defines the entire system's personality, how secure it is, how fast it is, and who it's built for. Choosing the right consensus model is literally the most important decision you can make. And this stuff really, really matters. BFT is what makes something like Bitcoin even possible. CFT is what lets huge competing companies work together securely. This technology is finally solving that age-old problem of how we all agree on a single truth without needing a big, powerful, and often expensive middleman to do it for us. It is the absolute bedrock for the next generation of the internet.
So, as our world becomes more and more decentralized, the really important question becomes a personal one. The next time you use a digital service, you might just find yourself asking, what's the engine of trust under the hood here? What consensus model am I relying on to keep the record straight?